Welcome to this deep dive into some fascinating machine learning research.
Glad to be here.
Today we're looking at a really interesting paper. It's trying to fix a pretty big problem in vision language models, VLMs.
Right, getting them to reason better visually.
Exactly. The paper's called Visual Web Instruct, scaling up multimodal instruction data through web search. And, for anyone tracking AI, this could be quite important.
Yeah, because it's all about the data.
Yeah.
We know VLMs are good at, spotting objects.
Basic perception stuff.
Basic perception, yeah. Answering simple questions about an image. But the complex stuff.
Like understanding a science diagram or maybe a multi-step math problem shown visually.
Precisely. Or even just applying some common sense reasoning to an image, that's where they often fall short.
And this paper says, hey, maybe the data is the bottleneck.
That's the core argument. We need better reasoning-focused training data.
Okay, so Visual Web Instruct. It sounds like they saw this gap. We have tons of text data that made language models amazing.
Yeah, I think come and crawl, things like that.
But not the same kind of massive, high-quality, multimodal data that mixes visuals and text for complex reasoning.
Right, and manual annotation is just too slow and expensive at the scale needed.
So their solution, Visual Web Instruct, is basically an automated pipeline to go out and find this data on the web.
Exactly. Find it, process it, clean it up, and make it useful for training these models to think, not just see. The automation is really the key piece here.
Okay, let's really dig into how they did it, the mechanics of the research. We can use that standard structure, right? Problem, solution, method, data, results.
Sounds good. Lay it out clearly.
So the problem, we've touched on it, but what did the paper specifically say holds VLMs back from complex reasoning?
Well, it boils down to the training data sets. The existing ones for multimodal reasoning, they're often limited.
How so?
Some are really specific, like figure QA is just about charts. CLER is abstract shapes and spatial stuff.
Okay, very narrow domain.
Yeah. Others might use synthetic data, which isn't always like the real messy world. And even ones like Science QA, which are broader, tend to be more maybe elementary level.
Gotcha. So not quite pushing the models towards higher level thinking. It's like trying to teach advanced calculus using only addition problems.
That's a good analogy.
Yeah.
You need the right kind of challenges.
So that leads to their proposed solution, this Visual Web Instruct pipeline. The goal is automatic generation of a big, diverse, high-quality data set from the web.
Right. Tapping into that huge amount of information online, but doing it smartly to get the reasoning-focused examples. And it's ambitious.
Definitely. Okay, now the methodology, the nitty-gritty. How do they actually do it? You mentioned 2 stages.
Yeah, stage 1 is basically mining the raw data from the internet.
Where do you even start with the whole internet?
Good question. They were strategic. They didn't just scrape randomly. They started with about 30,000 seed images.
Seed images?
Yeah, from a website called Steamass. It collects educational materials, math, physics, chemistry, engineering, biology.
Mm-hmm. So starting with content that's likely to be rich in information and visuals needing explanation. Smart.
Exactly. High quality starting points. Then they fed these seed images into Google image search.
Like a reverse image search to find similar stuff.
Pretty much. Find visually similar content out there on the web.
Yeah.
And that blew up the numbers. They got almost 760,000 unique URLs.
Wow. From 30K seeds to over 750,000 URLs.
Yeah, after filtering out some irrelevant sites and respecting, crawling rules, using a powerful tool like Google Image Search was a practical way to find relevant multimodal stuff at scale, which has always been tricky.
Okay, so they have this huge list of web pages. How do they get the actual useful info out? Web pages are messy, ads, menus.
Right. They use something called accessibility trees. It's basically a structured representation of the page content, kind of like what screen readers use.
So it strips away the visual clutter, navigation, ads, all that junk.
Exactly. It helps focus on the main text and image content, which is where the good stuff usually is.
Makes sense. And from these cleaned up trees.
They used a language model, Gemini 1.5 Flash, to automatically extract question-answer pairs.
So the AI reads the cleaned up page and pulls out potential questions and answers.
Yeah. They got a lot initially, about 420,000 pairs.
Mm-hmm.
And importantly, something like 60% of those had images associated with them.
But web data is noisy, right?
Yeah.
Not all those pairs would be good.
Absolutely. So crucial step, post-processing. Again, using Gemini 1.5 Flash, but this time as a judge.
A judge? How?
It evaluated the extracted pairs. Is this question actually meaningful? Is the image relevant and clear? Is the answer plausible?
A quality control filter, essentially.
Exactly. And that cut down the numbers, but significantly boosted the quality. They ended up with around 360,000 valid QA pairs and about 330,000 valid images associated with them.
Okay, so that's stage 1. Find, extract, and do a first pass cleaning of the data. What about stage 2, the dataset refinement?
Right, this is about making the data even better. 2 main steps here: answer refinement and answer alignment.
Answer refinement.
Yeah, this is pretty clever. For each question, they used a more powerful model, GPT-4O, to generate 4 different possible answers.
4 versions of the answer. Why?
To check for consistency. They then used GPT-4O again, this time to act as a judge, comparing those 4 answers.
Ah, so if the model consistently gives similar answers, it's more likely the question is well-defined and has a stable answer.
Precisely. They only kept questions where more than half the generated answers were consistent.
Oh.
It's a way to filter out ambiguous or problematic questions. This resulted in about 1.04 million QA pairs, because each question now potentially had multiple good answers.
That's a smart validation technique, building consensus. Okay, what was the second refinement step? Answer alignment.
Answer alignment. Here they compared the good GPT-4o answers with the original answer scraped from the web, if one existed.
Why compare back?
Well, they used another model, Gemini 2.0 Flash, for the comparison. If the GPT-4o answer and the original web answer disagreed significantly, they actually kept the original web answer.
Really?
The thinking was the original might have some specific context or nuance from the web page that the generated answer missed. But if they were consistent, they kept the generally more reliable GPT-4 answer. It's a careful balancing act.
I think quite a sophisticated pipeline. So after all that, what did the final dataset statistics look like? What is Visual Web Instruct?
The final dataset has around 900,000 QA pairs. About 40% are visual, meaning they have an image associated with them, using over 160,000 unique images.
Then the other 60%.
Text-only QA pairs. Still useful for training general VLM capabilities.
And the subject matter, still that science focus.
Yeah, broad coverage across those STEM fields. Math is the biggest chunk, about 62%, followed by physics, finance, chemistry, engineering. Makes sense, right? Those fields rely heavily on visual diagrams, charts, equations.
Definitely. And they checked it wasn't just memorizing benchmark answers, decontamination.
Yes, they perform standard decontamination checks against common evaluation benchmarks. Crucial step.
So a large, diverse, quality-controlled data set focused on reasoning, especially in STEM. Now for the payoff, the experimental results, did it actually work?
Seems so. They took existing VLMs, Mammoth HVL and Lava OV Mid, and fine-tuned them on this new Visual Web Instruct dataset.
Yeah.
Significant performance boosts. Lava OV Mid saw absolute gains of like 10 to 20% on some tough visual reasoning benchmarks.
10 to 20% is huge in this space.
It really is. And Mammoth HVL, when fine-tuned, they called the new version Mammoth HVL2. It achieves state-of-the-art results for models in its size class, around 10 billion parameters on benchmarks like MME Pro, MathVerse, and Dynamath.
Wow. So it beat other models, even potentially larger ones, just by training on this better data.
That's what the results suggest. It really highlights the impact of high-quality, reasoning-focused data. They also did ablation studies showing the data set itself was key, and it complemented other data sources too.
Okay, so summing up the key contributions, a scalable pipeline for getting this data, the data set itself, which they released, right? And the high-performing Mammoth HVL2 model.
Exactly. Pipeline, data set, model. A solid set of contributions. And making the data set public is great for the research community.
Now, maybe let's put this in a bit of historical context. How does this fit into the evolution of VLMs?
Well, early VLMs and the data sets they used like VQA or Doc VQA were really focused on perception, as we said. Object recognition, reading text and images, basic questions.
Getting the foundations right.
Yeah. But the ambition grew. People wanted AI that could reason about what it sees. And that's when the limitations of existing data became clear.
Those narrow data sets like figure QA or the simpler ones like science QA.
Right. They weren't enough to teach complex, multi-step reasoning. It's kind of like how NLP took off once we had massive web text data sets.
Like Common Crawl. The paper mentions Web Instruct for text, right? Trying to get instruction data from the web.
Exactly. This paper is trying to do something similar, but for the multimodal world, combining vision and language, which is harder, partly because finding relevant image-text pairs reliably at scale has been a challenge.
Until now, maybe? Using tools like Google Image Search seems like a clever starting point.
It's a pragmatic approach. leveraging powerful existing tools to bootstrap the collection process.
Okay, let's maybe crystallize some clear, non-repetitive points. What are the absolute key takeaways here?
1. The scalability and automation. This pipeline is way more efficient than manually creating data.
Huge advantage. 2.
The diversity. Pulling from the web across many STEM fields gives it breadth and covers different complexity levels, from homework problems maybe up to college exams.
Much richer than a narrow synthetic data set. 3.
The refinement process. That two-stage cleaning and consistency checking is critical for ensuring the data is actually high quality and accurate, not just big.
Can't just scrape and pray, need that quality control. And 4.
The results. The big performance jumps on tough benchmarks really show this data set works. It enables better reasoning.
And maybe a 5th point. The approach itself, supervised fine-tuning, is fairly standard, right?
Yeah, that's a good point. It's not some super complex new training method. It suggests others can potentially get similar benefits by using this data with existing models. Makes it more accessible.
So what about real-world implications? If we get VLMs that can reason better visually, what does that unlock?
Well, think about education. AI tutors that can actually understand the diagrams or math problems a student is stuck on.
That would be amazing, instead of just keyword matching.
Right, or analyzing complex scientific visuals, research papers, medical imaging maybe down the line, financial charts, understanding those visualizations more deeply.
Better insights from data. And you mentioned democratization.
Yeah, potentially. If this pipeline approach makes high-quality data more accessible, maybe smaller labs or researchers without massive resources can compete better and push the field forward. It levels the playing field a bit.
Could it even improve things like image search itself? Understanding the reasoning behind an image?
Possibly. If search engines understand the context and the problem depicted in an image, not just the objects, search could become much smarter. It definitely opens up interesting possibilities.
It really does. Which leads us nicely into our novel notions segment. Where could this research go next? Any interesting extensions or future ideas?
One area that seems really promising is active learning.
Active learning, how would that work here?
Well, instead of just starting with the Steamass seeds, imagine using the VLM trained on the first batch of Visual Web Instruct data to actively go out and find new images on the web, specifically images it finds difficult or confusing.
So the model identifies its own weaknesses and seeks out data to fix them, like a targeted exploration.
Exactly. It could be way more efficient at finding the really valuable, challenging examples that push its reasoning capabilities further. You could even frame it like reinforcement learning, reward the model for finding hard problems that lead to good new QA pairs.
An iterative loop of learn, find hard stuff, learn more. That's cool. It makes the model part of the data creation process.
Yeah, moving towards more self-improving systems. It's a very exciting direction.
What else comes to mind?
Another idea could be creating a sort of Visual Web Instruct Lite, but hyper-focused.
Light.
Meaning smaller.
Smaller seed set, maybe, but intensely focused on one really complex domain, like, say, advanced quantum physics diagrams or high-level organic chemistry structures.
So instead of broad STEM, go super deep in one niche area.
Right. Start with highly curated, expert-level seeds in that niche, then use the web search to mine everything related really deeply. You could potentially build an incredibly challenging data set for training expert-level VLMs in that specific field.
An AI specialist for quantum physics visualization.
You might even need to bring in other techniques for refinement in such a domain, like maybe knowledge graphs or symbolic reasoning checks to ensure the deep scientific accuracy.
That's fascinating. Building highly specialized visual reasoners.
These are just ideas, of course. Speculative.
Sure, for discussion.
Yeah.
But they show the potential this core idea unlocks, don't they?
Absolutely. It's fertile ground for future work. Okay, so let's wrap up this deep dive. The Visual Web Instruct paper seems like a really solid step forward. It directly addresses that critical need for better reasoning data in VLMs.
Yeah, the core takeaways are pretty clear. They've developed this scalable way to get high-quality reasoning data from the web.
The pipeline itself.
The data set they created actually leads to significant performance gains on tough tasks.
The results prove the data's value.
And it opens up some really interesting possibilities for the future, like that active learning or specialized data set idea.
We definitely recommend checking out the paper if you want the full technical details. We'll put a link in the description. It's worth a read if you're following multimodal AI.
For sure. And maybe a final thought to leave folks with.
Mm-hmm.
As we get better at automatically creating these massive data sets,
Yeah.
how do we really ensure they're not just massive, but also reliable, unbiased, and truly capture the kind of reasoning we want? Quality control at scale is going to have a huge ongoing challenge, isn't it?
That's a great point. It's not just about quantity, it's about the nature of the data and what knowledge or maybe even biases it encodes. Something to keep thinking about.